In the last example, we took a look at the idea of a cone, and we saw again that working with and understanding how the ellipses functioned really let us understand how the quadric surface behaved. So let's take a look here at example number 5. Again, we're going to go ahead and try to view this from each of the different perspectives of the axes. So if I was looking here down the x-axis, meaning again I replace x with some sort of a number, I'm going to end up with the following formula, and I can try to think about what sort of um, conic, conic section this is based off of. So here what you could see is that I kind of have a y squared over a 4 minus a z squared, and I move my x squared term over to the other side. And so I kind of see this looks like a hyperbola sort of formula. Notice again that over here, I might end up with the positive number. I might end up with a negative number. That's actually entirely possible. But either way, if I had to say divide both sides by a negative to get this side equal to 1, all that's going to happen is these values here are going to flip-flop which one's being added and which one's being subtracted. So overall, this will always and forever be a hyperbola. Okay. All right, well, let's take a look at what happens down the y-axis. So here I'm going to get x squared. I'm going to get plus a number squared over 4. Then I'm going to have minus z squared equals 1. All right, so in much the same way, I'm still going to be left here with a basic hyperbola type shape. Oops, this here is over 4. Again, this isn't surprising because all of the different surfaces that we're talking about here in examples 4, 5, and 6 are always going to be built from two perspectives as hyperbolas and from a final perspective as an ellipse. All right, if I look here now down the z-axis, this is where things get interesting. You can see that right off the bat, I'm going to have a basic ellipse sort of a shape popping up here. But if I replace z with a number, something really interesting happens when I try to move things over to the other side. So notice that when I do this here, I'm going to end up with 1 plus some number being squared. And this is really, really crucial to try to think through. This is the ellipses that I have, but I need to figure out, do these ellipses always exist? Do they sometimes exist? Are there times when they shrink to a point? Are there times when they stop existing altogether? What's happening here? Okay, so what I can start to see is that the only way, again, that an ellipse could fail to exist, right, when the surface would kind of stop existing, is if I had this value on the right side of my equal sign turn into something negative. But notice that that's never going to be possible here because I always have 1 plus a value squared. And the only time that an ellipse could ever kind of shrink all the way down to a point and kind of turn into just a single dot on the graph would be if I could get like my x squared plus my y squared terms to come out equal to 0. But notice that also can't happen because there's no way that a number squared can turn into a negative 1 if we're only dealing with real numbers. So what we have here is ellipses that always exist and don't shrink to a point. So what would it look like if I had something like this? What would this be? Well, this would kind of be a graph that I could kind of imagine looking like this. Here you can see actually kind of the hyperbola shape, and my ellipses would kind of be in here. So I kind of get like this nuclear power plant smokestack sort of thing going on here. And notice that the ellipses do get smaller and smaller and smaller as I head towards kind of like the center or the middle of this thing, but they never kind of go all the way down to a point like they did with the cone. Okay? So this basic shape here is what I refer to as a hyperboloid. This is a hyperboloid. And we're going to refer to it a little more specifically as a hyperboloid of one sheet, because when I look at this surface here, you could imagine that you could kind of create something like this out of, say, like a single piece of paper, if you will, right? It's one connected thing. And this will be different from when we get to the next surface, which we refer to as a hyperboloid of two sheets. Let's take a look at that. So here we're going to do the exact same thing that at least we did before. Let's take a look at this surface from different perspectives. So from down the x-axis here, I'm going to have minus a number being squared, and then I have minus a y squared over 4 plus a z squared equals 4. All right, so if I rewrite this a little bit, notice I could express this as, say, like z squared minus a y squared over 4 equals 4 plus some number squared. So overall, I can see again what I'm really getting here is a hyperbola. And the y-axis can be done much the same way. Here I'm going to end up with a negative x squared minus a number squared over 4 plus my z squared is equal to 4. And again, this is going to get me that basic hyperbola shape. I'm going to end up with 4 plus a number squared over 4. Basic hyperbola shape. Again, the interesting thing here comes when we get to our z-axis. And when we get here and we replace z with a number, we're going to have minus an x squared minus a y squared over 4 is going to then be added to some number squared equal to 4. All right, so let's think about what this is going to look like. Okay, so first off, I can recognize that if I just slid over this number being squared, this side over here on the left wouldn't fully look like what I normally see when I look at an ellipse, because normally when I look at an ellipse, I have a positive item added to another positive item. So what I'm going to do here is move over the number squared, but I'm also going to multiply both sides by a -1 as I do that. So what I'm going to end up with here is some number squared and then -4. Okay. Now, this does create that basic sort of ellipse shape, but again, I have to look at how the ellipses are behaving here. Are they always going to exist? Do they ever shrink to a point? What happens? Well, it's actually pretty easy here to first figure out when these ellipses shrink to a point, and they do indeed shrink to a point. That would, remember, would be whenever this side over here becomes 0, because that would mean that there's only one pair of x, y values that could ever possibly make x squared plus y squared over 4 equals 0. And that would occur whenever I plugged in for z, say either +2 or -2. So really quickly here, if I was to kind of start sketching out the picture, say at -2 and +2, my ellipses should have shrunk all the way down to single points. So I'll say here the ellipses shrink to a point when z equals ±2. But there's also some other things here that happen. Notice that if my value of z is too small, this right-hand side of the equal sign is actually going to become a negative number. Say, for example, if I plugged in z as a 1. So if I did that, then I would get x squared plus y squared over 4 is equal to -3. And there are no values of x and y that I could plug into here to get this left side to equal -3. So what this is telling me is that there are times when my ellipses are not going to exist at all. Specifically, you could probably narrow down exactly for what values this is going to take place. I'll state here that my ellipses fail to exist when z falls between two particular values. Notice here, if z is smaller than 2 or bigger than -2, I'm kind of not going to have an extreme enough z value so that the squaring of these values could overcome the 4 and maintain a positive number on this side. So what I'm going to see, though, is that once I get past the value of 2, like I get above it on the z-axis, or I go below it on the below -2 on the z-axis, that my ellipses are going to start existing again. So what I end up creating is something that kind of looks like this. So notice that this is going to be very, very similar to the previous pictures, except that now I kind of have two disjointed pieces. So it's not quite a cone, because a cone would say these pieces would have to stay connected. There's no kind of dead space in the middle. And it's not a hyperboloid of a single sheet, because now I could almost imagine having to create, or needing, 2 sheets of paper to kind of create this particular solid. So this quadric surface here is what we refer to as a hyperboloid of 2 sheets. All right. Again, it's super important to try to make sure that we understand that in order to successfully determine which of these surfaces we have to understand how we think through those ellipses. And so that's one of the most important things you can spend your time focusing on as you're trying to rehearse these ideas. Do you really understand how and why the ellipses are behaving in the way that they do?